Okay, in the last class we have already seen things like gradient operators, divergence and curl through tensor notations as well. We have also looked at some characteristics, and now we are going to talk about uh, in today's lecture is Gauss theorem. To be more precise, it is also called Gauss divergence theorem. Okay, and this Gauss divergence theorem is nothing but it relates a volume integral to a surface integral. Okay, and to see what relation it associates from volume integral to surface integral and what is the need for that, before that we should understand what these volume and surface and line integrals are. Okay, so the volume integral is nothing but it is the integral of over any function or any field. Volumetrically. Okay, let's suppose I have a field, I have a function field which is a function of x comma y comma z. Okay, and so this was your field. Let's suppose this is your coordinate system, and you have a field function, like you have everywhere you have points. Okay, and so this is a continuous function. You can say it will be a whole region filled with points with f x comma y comma z. Now in order to calculate the volume integral, what you do, you may take a small volume of cube with dx dy and dz. Okay, with dv volume, small dv volume, and you multiply this integral volume with the function, and you integrate over some specified region, in the sense that let's suppose I want to calculate the cube area of something like this. So let's suppose you have a bigger cube and I want to calculate the volume of the cube. Okay, now what I will do, this cube will have some function x comma y comma z. Okay, and I want to find what is the volume of this whole cube. So in order to do that, I will start with this elementary volume, in the sense that let me write that. So the total volume can be written as the function value of these cubes at this, like these surfaces values. Okay, or these surfaces values, which will be in the some function. So that function I will write fx comma y comma z. I will multiply with this infinitesimal volume dv, and I will integrate it through the whole domain. Okay, so this function value for, let's suppose for this cube, this function value must be, so you can you know that this your function values are specified as, let's suppose this is unity, so x is equal to 1, y is equal to 1, and z is equal to 1. Okay, so this can be specified by these planes, x is equal to 1, y is equal to 1, and z is equal to 1 planes, you can specify a cube. Okay, so this will be your so I know that for cube x comma y comma z is equal to 1, which I will substitute it here. Also this domain, I know that this domain can be written as a triple integral, and this dv can be written as dx comma dx times dy times dz. Okay, so this I can write in fxyz times dx dy dz, and now I can write my domains individually in x y z. So x is equal to, let's suppose 0 to, I went to 0 to 1, y dy is equal to 0 to 1, and dz is equal to 0 to 1. Now this should give me the total volume of the cube. So this is how the volume integrals are being generated or calculated over a specified function. So let me see that. So let's suppose 0 to 1, 0 to 1. So I'll take up this function first. So fx comma y comma z is equal to 1. So 1 dx. Okay, so 1 dx is equal to what is the thing? 1 minus 0. So leftover integrals are there. Again 0 to 1. This is 1 times 1 minus 0, y also dz, and then again dz is also integrated. So overall it is 1 unit, isn't it? Unit cube probably. So total volume you got. So this is how you are going to calculate your volume integrals. Not only volume integrals, you can also calculate surface integral. So surface integral can be written as your function, any function value, fx comma y comma z ds, and you should integrate it over the whole surface area in two-dimensional sense, let's suppose. Similarly, line integral can be written in terms of 0 to L fx y comma z, and this is okay. Now in fluid mechanics we actually want to switch between these three things very intermittently. Very now and then we want to switch between volume integrals. Somewhere in the fluid mechanics equations you may get volume integral, but you are not happy with that, so you want to switch back to surface integral associated with it. Okay, and you again want to switch back to line integral in sometimes you want to calculate some properties of it. Okay, and also in lower integrals you can actually visualize things better. Okay, all sorts of things are there in your fluid mechanics course. So this is a crucial property that Gauss, this particular physicist or mathematician, have come across, is he actually relates your volume integral to the surface integral. But the relation was not straightforward. So what he calculated mathematically, that the divergence of any vector field, the volume integral of, so this is the volume integral of any of divergence of any field. It can be vector, it can be, okay, it should be vector when you are taking divergence for any vector field. Okay, so there are three keywords here. So volume integral of divergence of any vector field. So this is a volume integral over, and it is being multiplied with the divergence of a vector field. And now this type of volume integral is is come out, it came out to be equal with surface integral. Basically you can also write q dot dA. So this, since this is dot product, okay, so you can think of as a surface integral of, so dot product of surface integral of dotted with the vector, surface integral in dot product, in dot product sense, over the area. Okay, this is how he has come up. So the proof is a bit tedious. I will not go, and this would be out of context of this particular course also. This proof will be highly mathematical. Into the mathematics part of it, we just will take the advantage of what these guys have proven, and they have proven that the volume integral of divergence of any vector will be the surface integral in the dot product sense. Okay, so what does this mean? So basically it means here, let's suppose you have a bigger volume, okay, and you took a infinitesimal volume inside the body. Let's suppose this is a body, okay, and you have a vector field over here. You have a vector field, I don't know, some like this, it is going across this, maybe something like this, maybe something like this, I don't know. So there was a field associated with it, and this field vector was q. This field vector was q, and it is actually essentially a function of xyz. That is why it is a field. Okay, it is continuous function in xyz. Now when the divergence of this thing over this, so basically this q is being thrown on this particular infinitesimal volume, the divergence of this q multiplied with dv and integrated over whole volume comes out to be the same q dotted with the dA. Let's suppose this is my dA, that surface I'm talking about, any surface. This is being dotted, and this is also integrated over whole surface. So everything is being summed up in the sense that in holistic sense. Okay, so this is an integral science, means you are integrating, summing all the smaller volumes over all the spaces. Okay, so intuitively it states that the sum of all sources of the field in a region, sum of all sources. So sources means, why does this source word come into picture? Source, the source word was generated, yes, generated due to there was a positive divergence, right? Remember we told that if del dot v, so like this one, you will have some heating was going on, and you will see that in some sense there was a flux density, positive flux density was there, right? So again, yes, positive divergence, sum of all those sources. So let's suppose I have all the spaces, and it is being summed all over of the field in the region, gives the net flux out of the region. Okay, so this is your, essentially this is your sum of all sources, and this is your net flux. Flux, you remember we have calculated the flux f dot dA. Okay, and it could be integrated over all area. That is how you calculate the flux. So overall net flux over the surface can be calculated either by, I mean, either by directly calculating this flux, or it can also be treated as the sum of all the sources uh, as a combined sense. Okay, and we can see that this Gauss divergence theorem has a great implication while we will be deriving our Navier-Stokes equation in later chapters. Okay, while we will be the fluid volumes, we are often interested in how much fluid is coming in and going out, or in some sense we are actually interested in the fluxes associated with it. Okay, not we generally, these things are not generally uh, measurable. I mean, this is hard to calculate. So we can since your equations are in some sort of volume integrals, so we will change it with fluxes associated with it, and this can be easily measurable and it can be easily observable as well. So that is why it is a easement of deriving Navier-Stokes equation as well. Okay, in tensor notation or index notation, it can also be written in terms of, so this is your dou q I by dou xi, so it means there is a summation sign. Okay, so obviously the summation sign means you will have a dot product between nabla operator and q, right? Remember, I times dou by dou x, j times dou by dou y, plus k times dou by dou z, dot product with qi or qi q1i q2j plus q3k, and if you do the dots, you will get the individual derivatives. Okay, that is why I sign over here. Times dv is equal to di qi. Obviously this is again a dot product, so you will have a summation sign, uh, ai qi, so a1 q1 plus a2 q2 plus a3 q3. This is something like this. Okay, nothing more into the notation part, but this Gauss divergence theorem, basically you should keep in mind that it has a very large physical implication in the whole fluid mechanics course. In this particular course we are going to deal with these sort of things. Okay, we'll take up one quick example. I want you guys to take a paper and pen and do this exercise for me. So it is given that by using divergence theorem, Gauss divergence theorem, uh, to evaluate this particular integral. So it is telling that you should integrate f dot ds. So ds is nothing but dA over here, surface. ds is nothing but dA over here, which is written. Okay, dA or ds, you can take it anything, where f is equal to sorry. So where f is equal to, f is a field function, vector field, which is given over by some function of x, y, and z, or a mixture of x, y, z. Some trigonometric functions are also there, and S is the surface of the box. So surface is defined. So where you have to check. Okay, surface could be arbitrary, but here it is telling that surface is given as the box with x values ranging from -1 to 2, y value ranging from 0 to 1, and z value ranging from 1 to 4. Note that all 6 sizes of boxes are included in X. Yes. Now can you calculate this surface integral? So please do it for me. Let's see. I'll wait for some time. Let's do this. Proceed. Anybody? Can somebody tell me how to proceed? Any one
सर
of you?
वॉल्यूम के
एग्जैक्टली सो अभी क्या है सरफेस का मुझे उतना पता नहीं है बट आई नो दैट दिस थ्री थिंग्स इन कंपासेस मी सम सॉर्ट ऑफ वॉल्यूम ओके सो इसको बेटर है कि हम लोग वॉल्यूम इंटीग्रल में चेंज
सर
करके फिर हम
इसको
कोशिश करेंगे
लिमिट में रखना है ना।
हाँ हाँ तो बेसिकली तो मैं थोड़ा हिंट दे देता हूँ तो ये मेरा सरफेस इंटीग्रल जो है सो दिस इज माई फील्ड फंक्शन डॉटेड विथ डी एस it can also be written in terms of volume integral okay the volume it is encompassing where this is nothing but del dot f देखिए divergence of this f times dv okay now it can also be written as divergence of f dv can be written as क्योंकि हमारा coordinate system x y z है तो dx dy dz I can write if my system would be polar or cylindrical coordinate system I could have done that what could I have done dr uh, r d theta and d phi something like that we could have done okay but here we will not do that we'll check upon those polar or cylindrical coordinate system later or spherical coordinate system later in later chapters but right now we should confine with our things with Cartesian coordinates so dx dy dz where dx can be integrated from x is written over here so x is written over here minus 1 to 2 y is given 0 to 1 z is given 1 to 4 now just evaluate this that's it right and this is easy for you but this was not easy why you don't know what your ds could be and where it could go but you know that your volume is being confined something like this so it is easy now to calculate so can you calculate for me you guys let's do this because you know this how this works del dot f and then do the integration and give me the results let's do this you guys are working
यस सर।
okay let's do this we'll wait for 2 3 more minutes because these things are important Okay, you guys following what I'm doing?
Yes, sir.
You also do in your copies also.
सर उसमें जो
हाँ,
J है वो ZY क्यूब है या ZY स्क्वायर है?
एक मिनट, वो जेड
सर
क्यूब है,
2Y
एक्चुअली जेड क्यूब है।
क्यूब है सर वहाँ पे।
थैंक यू थैंक यू थैंक यू। तो 3z स्क्वायर आ जाएगा। थैंक यू, यू गाइस आर फॉलोइंग इट सिंस। जेड वाई क्यूब है, जेड वाई क्यूब, सो 3z वाई स्क्वायर। थैंक यू। पहले हम लोग ये वाला इंटीग्रल लेंगे और इसको इवेलुएट करेंगे, बाकी रहने देंगे। Okay, anything you can do, either z side or x side. So what is the answer? I mean, this is straightforward. You have to do some integrations. Okay, or you can do one more thing. In order to avoid this particular thing, you put dz inside first. Okay, 1 to 4. So this is your function, dz first, so that this thing will not harass you much. Then dy and then dx. So dz is 1 to 4, y is 0 to 1, and this minus 1 to 2. You do this, then you will get the answer properly. Okay, what is the answer? You guys have come. So answer should come 67.5 units. Okay, so let's not work out for more minutes. So let's go switch to another theorem, which is called Stokes theorem.
Sir, what was the answer, sir?
67.5. Okay, let me finish this, then you can do it at your home. I mean, this is straightforward. You can, if you might be getting stuck somewhere, but this is just an algebraic glitch. So in Gauss theorem we have seen that it has related your volume integral with that of surface integral. Here Stokes theorem, what it does, it relates surface integral with that of line integral over open surface. So it takes upon, I mean, it relates surface integral over open surface. Open surface means you will have some open surface. You will have a it is not closed, such as ball. Okay, the ball is a closed surface. It should be an open surface to a line integral around the boundary curve. So let's suppose you have a cup. Let's suppose you have a cup. So this is sort of open surface, and this open surface, it relates this open surface with that of uh, the line integral around this edge. Okay, this is how it is related. So in order to do that, so here S is depicted for line integral lines, I mean differential line, and this is for differential surface. Don't confuse with S again. So this is your A, and this is your A, and then this is your line is S. Okay, generally displacements are written in terms of S. Okay, so this is your surface integral is related to line integral with that around the curve. So but here the catch is the surface integral is not that way related. I mean, in the sense that it is not divergentically related, but here your vectors, let's suppose it is associated with some sort of vector. Let's suppose this is your u vector field. So this u vector field, we need to first calculate the curl. So the curl of the vector field dotted with the surface, differential surface, dotted with differential surface is equal to the 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 vector field dotted with the differential line length, dl length. Let's suppose this is your dl length or ds length, and this is moved in the outer boundary of the thing. Okay, and this dA will be the surface area of the open surface. So this open surface area, if it is acted upon by some sort of u, then the curl dotted with that surface area, its integral must be equal to the u dotted with this dl, or maybe in the sense of line integral. Okay, this is how it is written. Again, the proof will be very mathematical. We'll not go into this will be the context of this course also. We just take a advantage of taking these things, I mean using these formulas, that's all. So the curl of the vector field dotted with differential surface area must be equal to the so this is another name is circulation also. So any function or any function value, so any field dotted with the let's suppose you have a line. Okay, this is your line that is going, or this is your curve that is going, and you have a vector field, and you dot with this thing with the lines, differential line, and you integrate it with. So basically this is, if it is a closed surface, then it is called circulation, otherwise it is not. But in general, your open surface will have the closed boundary, so this will again, it will be called as circulation around it. Okay, so the curl of vector dotted with the surface area must be equal to the circulation associated with the vector over the boundary curve, closed boundary curve. Okay, let us take a quick example, but this will be a bit tricky. Use Stokes theorem to evaluate this. Again, you have to evaluate the curl f del cross f dotted with ds. This ds is the surface area, so this must be equal to, the line integral will be a single integral. This here it will be double integral, since this is a surface. So this is double integral will be evaluated as f dot dl. We will take it as a dl, and L will be through that curve. Okay. Now let's see how the function values are given. So function value is given over here. Okay, and S is the portion. So S, what is the surface you are talking about? S is the portion of sphere of a radius r with z greater than 0. So how does it look like? So it would look like something like this. So let's suppose this is your x, this is your y, this is your z. So z, so your actual sphere would look something like this. Okay, something like this. But since this is z is greater than 0, so it is a half cut circle, half cut sphere. So it would look something like this. This would be this would be isn't it? Let's suppose you have a sphere which is cut along z is equal to 0, or this will be this, I mean something like this. पूरा सर्कल, पूरा स्फीयर ऐसा दिखता है मेरा, पर वो कटा हुआ है. ठीक है, ये मेरा अब सरफेस है. ठीक है, दिस इज माय सरफेस. नाउ इफ इट इज कट, व्हाट कुड बी माय कर्व लुक लाइक? ओपन कर्व, जैसे ये मेरा कप में, हमारा कप में ये कर्व दिख रहा था, यहाँ पे उसके अराउंड हमें सर्कुलेशन देखना है, क्योंकि वही दिखेगा हमें सर्कुलेशन डीएल के अराउंड. सो वो मेरा कैसा दिखेगा? वो ये वाला कर्व होगा, राइट, जो कि ऊपर से हमें कैसा दिखेगा एक्सिस पे. यहाँ इंपॉर्टेंट है एक्चुअली. सो एक्स वाई एक्सिस पे हमें कैसा दिखेगा? दिस इज माय एक्स, दिस इज माय वाई, लेट्स सपोज. सो वो कैसा दिखेगा? वो हमें एक सर्कल दिखेगा ऊपर से. ठीक है, उसके अराउंड ही हमें सर्कुलेशन करना है. ओके, दिस इज व्हाट वी नो बिकॉज दिस इज द कट surface. नाउ you have f given and you have a circulation. So this is what, this is some length dl or ds or dl. Okay, some length. Now can you figure it out? Now we have to do what? f dot dl करना है हमें, right? So basically dl in the sense, so L को हम क्या करेंगे, चूंकि अब ये मुझे दिख रहा है क्या, एक तरह का फॉर्म दिख रहा है, और हम एक काम करते हैं, इसको पैरामीटराइज करते हैं. ठीक है, सो हाँ ओके, हमें ये देखना है, और ये जो जाएगा मेरा z, मेरा कहाँ से कहाँ तक जाएगा. तो बेसिकली हम क्या करेंगे, इसको पैरामीटराइज करेंगे. ठीक है, पैरामीटराइज इन द सेंस, मैं सर्कल का इक्वेशन लिखूंगा r. ओके, सो तो सर्कल का इक्वेशन r एज अ पैरामीट्रिक इक्वेशन, t एज अ फंक्शन हम लिख सकते हैं r cos t, 4 cos t. 4 is the radius of this particular circle. Right, remember r cos theta, r sin theta, and z. This is how we write. So r 4 cos t और थीटा प्रोबेबली थीटा रख देते हैं हम लोग, ओके, थीटा डी थीटा हम लोग रखते हैं. सो आर थीटा के टर्म्स में हम लोग देख रहे हैं, तो आर कॉस थीटा, ठीक है, ये आई कैप प्लस 4 साइन थीटा जे कैप प्लस जेड मेरा जीरो रहेगा क्योंकि मेरा इसी प्लेन पे हम देख रहे हैं, जेड इज इक्वल टू जीरो प्लेन पे. सो दिस इज योर आर, ठीक है. एफ आर कैन ऑल्सो बी रिटर्न इन टर्म्स ऑफ एफ. अभी एक्स एज अ फंक्शन ऑफ एक्स वाई जेड है, इसको हम लोग एफ एज अ फंक्शन ऑफ आर थीटा लिखना चाहेंगे. दैट वी कैन एक्चुअली रिप्लेस विथ वाई को रिप्लेस कर देंगे आर साइन थीटा से. सो आर साइन थीटा आई कैप माइनस एक्स आर कॉस थीटा जे कैप प्लस आर वाई है मेरा आर साइन थीटा टाइम्स r cos theta whole cube k. So this is your now function. So this function dotted with this r, okay, and now you have to integrate theta from 0 to पूरा एक रोटेशन मुझे मारना है, ठीक है. तो 0 to 2 pi. If you do that, you'll get the answer. So this was a bit tricky, but you have to do that. So straightforward we cannot do. Agree?
सर
हाँ हाँ.
सर एक बार फंक्शन वापस समझा देंगे.
So this is not dl, this is dl के बदले में dr लिखते हैं हम लोग. So this is your dr, ठीक है. So ये dr क्या होगा एक्चुअली में? Okay, so let's suppose this is my point and this is capital R distance from here. So capital R is 4. Okay, so इस point का x coordinate क्या होगा? So if it is moved around theta, so if this is d theta and if it is moved around theta, so this is your r cos theta, ये मेरा i डायरेक्शन में है, एंड r साइन थीटा j डायरेक्शन में है ना, किसी भी पॉइंट पे. अब ये पॉइंट क्या हो रहा है, मेरा रोटेट हो रहा है सर्किल में पूरा. तो मैं क्या करूँगा, जो मेरा dr जो चीज़ है, dr चीज़ को पैरामीटराइज करेंगे. dr को मैं बोलूँगा कि ये रोटेट हो रहा है 0 to 2 पाई, ठीक है. तो ये फंक्शन वैल्यू हम यहाँ रख देंगे, r साइन थीटा आई माइनस आर कॉस थीटा जे प्लस डॉट 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 जो भी है के टाइम्स ये वाला 4 कॉस थीटा आई प्लस 4 साइन थीटा जे प्लस 0. नाउ डॉट प्रोडक्ट करने पे और टाइम्स मेरा टाइम्स दो. सो ओके, आई एम रियली सॉरी. सो दिस वुड बी times dr. Wait a minute. So this times this is 16 and now dr is equal to d theta. So now everything is converted to d theta. So I am also getting confused. I will check upon it because this is a bit tricky, but in the sense that we cannot directly do this operation f dot dl. We cannot do it. We can we do it in a Cartesian? Let me also think about it. So I will maybe probably in the next class I will be able to answer. Can we do it in Cartesian only? Or and then I will also get back to you. Okay, so let's not talk more about it. Let me also check. Before that, I just wanted to show you that in the next class, we'll start this kinematics chapter. That is, we'll be dealing with introduction to kinematics. So kinematics is associated with the, what do you mean by kinematics of any kinematics? So it is, kinematics is a ideology where we are interested,
Motion of particle.
exactly, interested in uh, path or motion of the particle without knowing that uh, why it is moving. It means it doesn't care about the forces. Okay, so it is just telling the answer of how it is moving, how a particle is moving, rather than why it is moving. So we will not ask why question here, we will ask how question, how it is moving, and why question will be tackled in your dynamics part. Okay, so it will associated with Eulerian and Lagrangian descriptions, whether you will, in the Eulerian approach you will fix your control volume, in a Lagrangian approach you will you will keep yourself, your frames on to the particle, and you move around, along with particle. There are certain streamlines, path line, timeline, and stick lines. We will look into the fluid motion in order to visualize the fluid motion appropriately. We'll also look into the linear strain rates, shear strain rates, vorticity circulation, kinematic consideration of parallel shear and vortex force, vortex flows, stream functions, and polar coordinates. We'll tackle these uh, things. Okay, and I will look into this particular example again, and we'll get back to you. Okay.
Sir,
Hmm.
sir, can you upload all those videos that which are not uploaded yet, so we can revise in weekend, sir, and we will
Okay.
be prepared for next semester.
Okay. Today I will do that.
Okay, thank you very much, sir.
Okay.